Hello everyone, welcome to my presentation. My name is Jan Hesse and I'm the lead developer of TwinMesh. Today I'll cover the fundamentals of TwinMesh, its core workflow and highlight key new features in TwinMesh 2026. I hope you find it insightful and I'm looking forward to sharing some perspective with you. As you can see on the title slide, it offers a brief preview of the wide range of applications our software supports. Before we dive in, I'd like to briefly introduce our company. I've been working for CFX Berlin since 2004. Since 1997, CFX Berlin has provided simulation software, solution and services across fluid mechanics and thermodynamics, electromagnetics, structural mechanics and coupled physics. After many years as an ANSYS distributor, we transitioned to Siemens SimCenter in 2024. We made this change because we see greater potential in the SimCenter product roadmap, an important advantage for our clients and a crucial enabler for TwinMesh development. We also distribute Flownex, ParticleWorks and of course our own product TwinMesh. For all products, we offer training and we supply the necessary hardware. Beyond distribution, we use these tools to deliver projects on behalf of our clients. In research and development, we conduct research projects and develop software such as TwinMesh. Now let me introduce TwinMesh. TwinMesh was developed by CFX Berlin to enable high-quality CFD for rotary positive displacement machines, for example screw compressors, gear pumps or low blowers. It brings all the required steps into one unified end-to-end workflow so users can work efficiently and focus on the physics instead of manual meshing and repetitive CFD setup tasks. The workflow consists of three main steps. CAD import to extract the fluid volume and divide it into stator part and working chamber part. The second is meshing, where the stator mesh is generated using SimCenter STAR-CCM+, and the working chamber mesh is generated using TwinMesh specialized meshing strategy. Third one is setup, solving and post-processing, because TwinMesh automatically generates templates for STAR-CCM+ setup and post-processing, allowing users to start simulation runs quickly and analyze results consistently. So where is TwinMesh used? TwinMesh is used across a range of rotary positive displacement applications. Key areas include screw compressors and expanders, screw vacuum pumps, gear pumps, G-rotor pumps and many more. We are proud to support leading companies working in these applications. Many of our clients have used TwinMesh for years and value its reliability and efficiency. On the right hand side you can see some of our customers using TwinMesh. So what are the challenges in simulating rotary positive displacement machines? Let me illustrate this with a screw compressor, as shown on the right. The compressor is cut open, so you can see the working chamber. There are two intermeshing rotors. Due to the rotational motion, the flow volume changes continuously. Additionally, there are very thin clearances between the rotors themselves and between the rotors and the housing, in both radial and axial directions. Because the flow volume is time varying, a transient simulation is required. The fluid behavior can be very complex. In compressors, compressibility is essential, and with high pressure and temperature, real gas effects become important. In pumps, cavitation must be considered. On the structural side, thermal deformation affects clearances, which could lead to leakage losses. Altogether, These factors impose specific requirements on the CFD. Now let's look at the discretization options for the flow domain and why TwinMesh is needed. There are several meshing approaches, each with different strengths and limitations. For overlapping meshes, like immersed boundary or overset, a background mesh represents the working chamber without the rotors, and the foreground mesh describes the rotors. During the simulation, the rotor mesh rotates. The solver determines the overlapping volume, applies momentum sources or combines the meshes to calculate the impact of the rotor motion to the fluid. This meshing is simple, but there are drawbacks. Near wall accuracy is limited, boundary layer effects are hard to capture without very fine cells, and the models become large or runtimes increases. And of course the stability issues can occur. With remeshing, a new mesh is automatically generated as the geometry evolves, resolving the domain at each time step. Accurate small radial axial clearance require very fine resolutions and often extremely small time steps to maintain mesh quality, leading to high computational cost. Using mesh deformation, the mesh topology remains fixed. Only the node position are updated at each time step to follow the rotor motion. This can deliver efficient calculations, good gap resolution, and full model support. However, creating a suitable deformable mesh for complex clearances typically demands significant manual effort. This is precisely where TwinMesh helps by automating working chamber meshing. And that's why we developed TwinMesh. It uses the mesh deformation approach and automates the meshing process. As you can see in the animation on the right, TwinMesh pre-computes the node's position for every time step before the CFD run, ensuring consistent mesh quality throughout the motion. It generates high-quality hexahedral meshes tailored to narrow clearances. The red markers indicate control nodes. These nodes are updated at each time step, while the meshing topology remains unchanged. During the simulation, the CFD solver reads per time step files with the updated node positions. Let me briefly summarize the main advantage of using TwinMesh for the CFD of rotary positive displacement machines, before I show a short video of the workflow. High quality hexahedral meshes accurately capture the working chamber and thin clearances. TwinMesh pre-computes node positions for all time steps, ensuring consistent quality before the CFD run. The mesh quality can be pre-validated. In combination with Siemens SimCenter STAR-CCM+, this enables fast, stable and reliable transient simulations. To automate the workflow, TwinMesh provides ready-to-use templates for setup and post-processing, so you can go from cut to results very quickly. Now let's take a look at how TwinMesh works in action. Here you can see the mesh of the working chamber generated in TwinMesh. In this short video, you will see the workflow and how our software simplifies the process for our clients. TwinMesh integrates seamlessly with SimCenter STAR-CCM+. We start by creating a new TwinMesh project. From TwinMesh, we launched SimCenter STAR-CCM+ to prepare the geometry. In STAR-CCM+, we extract the fluid domain, split it into the stator and the working chamber, and generate the stator mesh using STAR-CCM+ meshing. Next, we export the rotor curves profiles from STAR-CCM+ and import them into TwinMesh. In TwinMesh, we define the machine-specific parameters and meshing settings, then generate the working chamber mesh and check its quality. TwinMesh exports all meshes as well as macro templates for CFD setup and selected post-processing task. Once the CFD setup is completed, you can start the simulation run right away and review the predefined plots and scenes. Now I'd like to show some simulation results that illustrate typical tasks and user benefits. First, rotor design is critical. With TwinMesh, you can modify rotor geometry to assess its impact on machine behavior, covering performance, cavitation risks, and leakage. Likewise, you can modify the housing to study how inlet and discharge flow affect efficiency, pressure losses, and pulsations. Both examples are low pumps. In this example from Hugo Vogelsang, the inlet geometry was varied to quantify its effect on efficiency. In addition to visualizing the flow field within the volume, time-resolved information is necessary in order to compare the results with measurement data or to better understand the effects of pulsation or noise emission. Here you can see two animations of the velocity field in a G-rotor and a low pump. Elevated velocity in the thin clearances highlight leakage flow paths which reduce volumetric efficiency. On the compressor side, we show a screw compressor and a screw vacuum pump. The screw compressor on the left is simulated with a single-phase gas model. For oil-injected screw compressors, you can set up a multi-phase simulation which uses gas and oil. The rotors on both machines can feature high rep angles or even variable pitch, which raises the demands on the meshing. TwinMesh's deformation-based workflow handles these geometries robustly. And finally, here's an animation of a simplified scroll compressor. One scroll orbits around the center while the other remains fixed, forming moving pockets. Gas progressively compressed as the pockets moved inwards to the central discharge port. But that's not all. Here are some additional TwinMesh capabilities. If you have rotor deformation data, for example bending or thermal expansion, you can modify the working chamber mesh relative to the ideal cut geometry. This changes clearance sizes and therefore leakage, allowing more realistic performance predictions. For multi-stage machines, you can combine different TwinMesh projects into a single simulation case to study interstage interaction and pulsation effects. For scroll compressors, you can include reed valves to prevent backflow into the working chamber, which can improve efficiency. We are constantly enhancing TwinMesh and adding new capabilities to meet our customers' evolving needs. Let me now explain some of the new features in TwinMesh 2026. The main focus has been on automating the workflow with the goal of integrating TwinMesh into the work process and thus reducing manual effort. Furthermore, this also reduces the risk of errors caused by incorrect import. As a result, the entire process can be accelerated, increasing the overall output. The basis for automation is the possibility to import and export the TwinMesh setup via an XML file. This enables both manual and automated modification of the setup using a text editor or an external tool to modify the XML file. The second new feature is that TwinMesh can be started in batch mode and its behavior can be controlled via command line arguments. This is an optimized method to increase the mesh quality for rotors where the rotor curve loop has sharp edges. For example, for highly twisted rotors in vacuum pumps. It reduces instabilities when using non-default mesh settings. High mesh quality is crucial for reliable CFD calculations, as poor mesh quality can lead to numerical errors, convergence issues, and inaccurate simulation results. By improving the mesh in these critical regions, the robustness and accuracy of the TwinMesh analyzers are significantly enhanced, ensuring that simulation outcomes are both meaningful and trustworthy. There are also many additional features that further enhance TwinMesh. For example, new options for modeling eccentric screw pumps, more flexible interface generation, and advanced setup definition tools. These enhancements make TwinMesh more versatile and user-friendly across a wide range of applications. For more information, please feel free to visit the links provided. Thank you very much for your time and attention. And now I'd like to show you a brief live demonstration of TwinMesh using a low pump example. After opening TwinMesh, you can select the type of machine you want to use. In this example, we choose a low pump. The first step is to import the rotors into TwinMesh. Here we are importing an IGES file that was previously exported from SimCenter STAR-CCM+. Alternatively, you can also import CSV files. Next, you need to assign the imported curves, defining which curve represents rotor R1 and which one represents rotor R2. On the left, you see rotor 1, on the right is rotor 2. In the tree view on the left, select the settings area. The detailed settings are displayed below. Here you can specify values such as the number of lobes for each rotor and of course the axis position. The imported geometry is without clearances by default. TwinMesh allows you to define an offset to the rotor curve if needed. The casing curves are not imported, but can easily be created within TwinMesh by defining the casing radius. Between the two rotors, additional curves are generated that surround the interface curve. The interface curve defines the contact line between the meshes of the left and the right rotor. Once everything is set up, you can check the rotor motion. Now we move on to the meshing. You can adjust the global maximum element size and also specify the number of nodes along the interface curve. In the radial direction, from the outer casing to the rotor side, we typically use 20 elements. Now you can generate the mesh for the first rotor position If you need higher boundary resolution, you can set the height of the first element accordingly. This helps us generate a boundary layer near both the rotor and the casing curve. Here you can see the refinement. After generating the mesh, you can check its quality. Usually the minimum quality should be above 18 degrees, which is already achieved in this case. Actual gaps can also be specified, for example with a value of 100 micron. You can set the shaft diameter and define additional meshing parameters, just like for the main mesh, such as the number of radial elements and creating extra gap meshes. Each actual site can be defined differently. You can also check the quality for the gap meshes. You then need to create the meshes for all rotor positions and check their quality. Since this process can take some time, I will now open a finished project so you can see what it looks like once all meshes have been generated. For the full 3D mesh, you can specify additional parameters in the actual direction, such as rotor width or wrap angle. As you can see, the mesh quality is sufficient for each 2D mesh section. Next, let's move on to setting up the simulation case. In TwinMesh, you can easily predefine the CFD simulation setup using a template in the background. This enables you to quickly specify the main parameters of the machine for a fast and efficient setup. You can define the speed of rotation, inlet and outlet pressure, and all necessary settings for running the solver. Once everything is ready, simply export the meshes and start the solver GUI. TwinMesh will then automatically open SimCenter STAR-CCM+. All the meshes and the setup definitions are transferred automatically. Now you can see the 3D model. TwinMesh provides a range of predefined scenes, plots, and monitors, so you can quickly start evaluating your results. Of course, you have many parameters available to adjust and fine-tune the CFD setup as needed. This allows you to run the CFD simulation efficiently and review the results as soon as the solver has completed. A key advantage of SimCenter STAR-CCM+ is that you can monitor results even while the solver is still running. In this example, you can watch how the velocity changes at each time step.